Welcome everyone. In this video I'm going to show you another type of encoder. So in my previous videos I've been working with these two types of encoders. A simple rotary encoder, this specific type is with a switch. And then also with a absolute encoder with 128 different positions and 10 pins. So these two guys work very nicely when you want to control a stepper motor, for example, or you want to navigate in a menu on a display, and so on and so on. So you can use them for different kind of things. But then I have these two guys, they are identical. This specific type of encoder or CNC hand wheel or pulse encoder was recommended by one of my viewers. So thank you for the recommendation. I bought these and they came recently after a lot of traveling. So I will show you how this thing works, what are the principles, and how you can apply it for a simple application to move a stepper motor. So as its name suggests, CNC hand wheel, this is used in CNC machines. And it is used to move the axis. And usually they come in some sort of a remote controller panel or box. So there are some other buttons with it, but here it is just directly connected to the microcontroller. So this particular thing has 100 steps. There is a notch here, and you can align the numbers with it, and one revolution of this wheel will produce 100 pulses. And then we have the back side of it. So VCC and the 0V is the power supply. So the input voltage should be 5 volts. So VCC goes to plus 5 volts and the 0 volt goes to ground, obviously. And then we have here A and B, which are the output terminals. So both of these terminals produce square waves, but the trick here is that one of these square waves are shifted related to the other square wave. So if you turn this thing clockwise, then A comes first, so you will notice the square wave from the A output earlier, and then after roughly half square wave, the B also shows up. I will show you some pictures when I show you the code. And if you turn this thing counterclockwise, then the opposite happens. So the B emits or produces a square wave first, and then after half square wave, roughly, the A also outputs a square wave. So you have a shifted square wave. And you can actually write a quite compact and smart code to detect these two alignments and detect whether you turn this thing clockwise or counterclockwise. And this is like a very simple principle, so it's very easy to code it and very easy to apply it for stepper motors. So what you see here with my system is that I have my favorite microcontroller, or one of my favorite. It's an STM32, but I cannot emphasize enough that you can replace this with an Arduino because the code works in the same manner. You just have to change the input pins, but I will explain everything. So we have our microcontroller, and there are, let's say, 3 peripherals. One is the encoder here. We have an OLED display just to show the number of steps or number of clicks in this encoder. And then here we have our regular stepper motor controller, which in this case is a DRV8825 controller, but you can replace this with any type of stepper motor controller which receives steps and directions as input signals. You should check this video in the corner where I explain how you can replace this stepper motor controller with any type of stepper motor controller or with any of the most popular stepper motor controllers. And then I have this tiny stepper motor here with a small zip tie here, so you can see how it is positioned. So let's jump to the demonstration, and I will just wire up everything. So we need a power supply, and now I'm just supplying 12 volts to this board. So this is now connected, and then I connect the USB as well. So now it's done, and I wrote this code in a way that it will not show anything on the display as long as I don't start to move the encoder. So I just move once, and then you see that 1 shows up. So now I try to do a full rotation, and I know it's not visible, but the notch is here in this place. So now I try to rotate a full revolution, clockwise direction, and then this should be at 101. And now I did a full rotation, and this is at 101, and since the microstepping setup here is 400 steps per revolution, then this went 1/4 backwards. I just wired this and coded this in a way that I did not care about the direction of this, so that's why I rotate this clockwise, but this goes counterclockwise. But it is just up to the wiring. I just want to demonstrate this thing to you, how it works. But you can see that this works very simply, and as long as you don't rotate this violently, you can register all the steps with this very simplistic code, and this will do the steps very easily. So I just rotate this 3 more rounds. I will check the notch's position here. You can see this is the notch, what I'm talking about, and then that thing is here. It's positioned in a silly way. So I do 3 more rounds, and then this let's say pin has to return here, and this should be 401 roughly. So this was 1 rotation. This was 1 more rotation, and then the last final is here. And you see that this did a full turn. And now I just try to rotate this randomly. So you can see that the stepper motor follows it very nicely. And of course, if I rotate backwards, it does the same. So it perfectly mimics the position and the rotation of the hand wheel. So this is very handy. So now what it does is that we send out the square waves from this thing. It is getting captured, or they are getting captured by the microcontroller, and then the microcontroller prints the number of steps here, and also does the number of steps on the stepper motor by sending out some pulses to this controller, and then the controller will do the rest of the job. And here comes a nice trick. So if you know something about the principles of a stepper motor controller, and now you know the principles of this, then you might think about something. So how this works is basically you send some high frequency square waves to the inputs of the stepper motor controller, and that is being converted into higher voltages, or not converted, but it switches the chip on this board, and then a higher voltage and higher current signal goes to the stepper motor, and the stepper motor, or the coils in the stepper motor, are being powered, and based on the configuration of the output, it will move to certain directions, counterclockwise or clockwise. So the thing is that this receives a set of square waves with some certain frequency, and then the frequency will determine the density of the steps. And what this thing does is it outputs square waves, and the frequency of the square wave will depend on the frequency of the rotation. So if you do it slowly, gently, then the frequency is low. So the displacement between the squares square waves is larger. But if you do it vigorously, then the square waves are closer to each other and also they are narrower. But then this suggests something. So now if I remove this step and direction pin from the stepper motor controller and I put it somewhere in the board, and if I remove these two pins from the CNC encoder and connect here, now the only connection between the microcontroller and the stepper motor driver is just the enable pin, but the wheel is not connected to the stepper to the STM32 by any means. It only receives the power supply from it. It's a 5-volt output, but nothing else. So when I rotate this, then the motor should move, and then the numbers will not be updated, of course, because the connection is aborted, or the connection is cut here. But what you can see, it's a very funny stuff that you can omit the microcontroller. But of course you don't have the feedback on the steps. But as you can see, I can directly control the stepper motor driver with this hand wheel. And this is very good, because then if you don't want to do anything with the number of steps, for example, you don't want to display it in this fashion by reading this output, then you can just directly connect the output. So technically the A and B goes to the step and the direction of the stepper motor driver, and as you can see, it works, and it works in both directions very nicely. And you can play around with the speed, of course, because now I have a certain microstepping. I just don't remember what are the microstepping setups, but I just changed the stuff, and now I think I went to 200 steps per revolution, because now it goes much more faster both directions. So now you feed a direct signal from the pulse encoder to the stepper motor driver, and that drives the stepper motor. And you can change the speed by changing the microstepping. So if you have a low microstepping settings, like 200 or 400 steps per revolution, then this will be faster. But if you crank it up to, let's say, 1600 steps per revolution, then this will be slower. I don't know what will be this value. I will write it on the video. But now I have the MS2 and MS3 on high, and the MS1 is low. And now you can see that I have to struggle with this, because the microstepping is much higher, so this goes more slowly. But this also suggests that you can move more precisely. And it works both ways. So what I try to show you here is that you can use this encoder wheel, and you don't need any programming knowledge to control a stepper motor in a very precise manner with an external hardware, which is basically just a knob or a wheel. So that's how it works. And now comes the question that how you can know the position and so on. So at the end we can introduce the microcontroller again, and we can put an encoder on this or on the mechanical structure that you control and read the signal of the encoder, but that will be a different video. But here I just wanted to show you that by using this wheel you can directly control the stepper motor driver, or you can send the signals to the microcontroller, process them, display it on a display, and then send the further signals to the stepper motor driver and then drive your stepper motor. So there are two options. But now I was focusing more on the coding part. So what I want to do, I go to my computer. First I show you the output of these things and explain you how it works. And then I will show you the code, which is a very short code, and it contains everything which is the processing of this signal, printing on the display, and sending the data to the stepper motor driver. So let's go to my computer and let's go through the coding behind this thing. So before looking at the code and explaining everything, I would like to explain the output signals of this encoder. And these are the two examples when I rotate it in clockwise and rotate it in counterclockwise direction. And what I start with is the top picture here. So the channel 1 is the A output and the channel 2 is the B output. And what you can see here, and this will be very important when we try to code this signal recognition or something like that, is that when you rotate this thing in clockwise direction, then the A signal goes high first. So there is a rising edge here, and then roughly after half signal width, the B signal also goes up. And then of course both of them goes down, and when there is another click, so let's say here we are at the 0 position, where there is another click, then A goes up first to high here, and then after a half signal the B also follows it. So what you can see here is in clockwise direction A is high first and then B follows it. And then if we go to clockwise counterclockwise direction, this is still the A and this is still the B, then you can see that the B goes high first and then it stays, and after roughly half pulse width or wave width, the A also follows it. So this will suggest us how to code the things and how to recognize the signal. So technically what you see here, I try to draw it in a quick sketchy way. So this will be our A signal, and then we just shift it. So they are at the same voltage in fact, but I just shifted up the or shifted down the A channel by 2.5 volts roughly. So what you can see here is that this is the A channel and we went counterclockwise, so the B channel is going up a bit later. So for example, if you do this with an interrupt, what I apply in my code is that you always have to observe the interrupt on the A output. So you just need one interrupt pin. This is very good if you are an Arduino user, because then you have limited amount of pins for having interrupt as an input. So what you see here is that A went up, so we just detect a rising edge of the A signal, and then quickly after that we have to look at the B signal. And if you look at it, then when this is high, so when A equals 1, that is basically this moment, or when A has a rising edge, then you have to read what is B, and you see that B is still 0. And then if you go down here, so again we have our A signal, but now the B looks something like this. I forgot the B here. So again we detect the rising edge of the A, so here A equals 1, and I just write an R and E here, so this is rising edge. So when there is a rising edge on the A signal, we have to read the B, and you see that B equals 1. And then you automatically see the two different solutions for this signal detection. So one case, I just try to put it in the middle. So case number 1 is A equals 1 and B equals 0, and this will be the clockwise rotation. And case number 2 is when A equals 1, then B also equals 1, and this will be the counterclockwise. and we just have to code these two conditions into a few lines, and we will be able to see the number of steps, and we will be able to detect the direction as well. So as you can see, the output signal of this is very simple, and it's quite easy to understand how it works and how we should interpret the signals and how we should code. So now you see the two different types of waves or signals which are coming out from the A and B pins. So let's jump to the Arduino code now and look at the code itself, how it works and how we can implement all these things. So this is the Arduino code, and it's really simplistic. I uploaded my code to an STM32, so the definitions of the pins are a bit different, but you can just choose any pins that you have on the Arduino, and this code will work in the same way. So just make sure that if you are using an Arduino, you just define the pins according to the standards of the Arduino. So I will show you what I mean later. So we need a few libraries, which is the wire, and a few libraries for the OLED display. And then we start with some code which just borrowed from the standard library for the OLED display. So actually, if you have these kind of libraries here, they have some examples. So I just lifted a few lines from those examples, and then I just copy pasted those, so you can just use it as it is. And for pin A and pin B, I used the PB10 and PB11 pins on the STM32, and then I just put a few comments here. So the behavior of the decoder is the following. If you have counterclockwise rotation, then the B wave comes first. If you have a clockwise direction in the rotation, then the pin A comes first, or the pin A's square wave. And as I showed it in the example, you can directly connect this encoder or the output of the encoder to the stepper motor driver circuit. So we can skip the whole microcontroller thing, but of course we will not have any kind of feedback from the amount of steps we did, or the amount of clicks done on the pulse encoder. So I stored the number of clicks in this variable, and I also stored the previous number of clicks. I will show you why, but with this we can have a more smarter update for the OLED display. And then we also need a timer for the OLED display, because I don't want to update it with every clicks, because that might be a bit overwhelming for the microcontroller, and it might cause lags. And then we have our favorite library, of course, the Axel Stepper library. So we have the PA9 and PA8 for the pulse and direction pins, and here you have to pay attention that now, as I'm using the STM32 microcontroller, I define the PA, and also here I define the PB. But if you are using an Arduino, these kind of definitions are not needed. So you just write 1, 2, 3, 4, 5, 6, whatever number is your selected pin for this purpose. And then I also have an enable pin for this specific stepper motor driver, and I chose it to be the PB12 pin. So then we enter the setup part. So of course we use the internal pull-up resistors of the pin A and pin B pins, and then we define the pin A as an interrupt pin, and the interrupt will point at the pin A interrupt function, and it will be triggered when there is a rising edge on the A pin. For testing purposes, I was using the serial port just to print out some messages whenever a click is detected and so on. So here I started the serial, and just to make sure that there is a communication between the computer and the microcontroller, I just printed a random message. And then again, we are using just some standard code for the OLED display. So you just copy paste everything and use it as it is. If you are not satisfied with the font size, what I mean is if it's too large, then you can change this to 1x like this, but I would keep it at 2x because this is a very small display and it has very tiny numbers, so 2x is a bit more readable. And then we just update the value of this variable to the current passed time in milliseconds, so we will be able to compare some date or some time in the future to this value. And then we have just some standard setup for the access stepper library and for the different parameters for the stepper motor. So the set speed and set max speed is the same value. Actually, these methods or functions depend on the functions that you choose to move your stepper motor, but I define both to avoid any kind of confusion. And I have a relatively large value of acceleration, but since we move the stepper motor step by step, this will not make any difference in this application. Since we have an enable pin, we have to define it as an output, but here I want to use the occasion and tell that some viewers were confused about the output pins of the access stepper library. You don't need to define the pins used for the stepper motor control as an output because it is contained in the access stepper library. So if I go back here and I have this definition for this stepper instance, I have the PA9 and PA8, but when you put it down like this and you write it like this, the access stepper library will make sure that this and this guy here is an output. So you don't need to define them as an output again here in the setup part. But the enable pin is a separate story and you have to control it manually from the code. So here you have to put it as an output, and then you also have to control it. So I put the value of this to low, which in this case it means that we enabled the current for the coils of the stepper motor. Then the loop is also very simple, so we have a show LCD function, and then we have this stepper.moveTo, which is providing an absolute movement. And then this part says that if there are steps to do, like here, so the distance to go is not does not equal to 0, then we run to that position and also print the LCD. So we flip this variable, but there will be some other things which will maybe hinder the updating of the LCD or OLED. So let's go to this part where we triggered the interrupt. So let's say the square wave appeared on the input of the A pin. So when we detected the rising edge, then there is an if-else statement. So we have to read the pin B, and in this case we start with the pin B equals 0 condition. So if the pin B is low, that means that we are at the beginning of the pin A rising edge, and at that time, if we rotated the encoder in clockwise direction, then the pin B should be still low, as you can see it on the picture. So then we know that we went in clockwise direction, and for us now that's the positive direction. So the number of clicks will be increased by 1. And here as a debug, I also printed this, but this is a bad practice. So this should be commented when you finalize your code, because in an interrupt you don't want to put, for example, delays, and you don't want to print on the serial port. So this was just for a demonstration. So we had this condition that the pin A was high due to the current rising edge, and at that point when the rising edge was detected, the pin B was low. So that was here. And now what happens if the pin B is high? So it equals 1 when we detected the rising edge. So that is the else part of this thing. So if the pin B is also high, that means that that wave already occurred So it was already high when we detected the rising edge of the A signal, as you can see it on the picture. And that means that we rotated the encoder in the counterclockwise direction. So with that, with our, let's say, reference system, the counterclockwise direction is a negative direction, so we decrease the amount of or the number of clicks. So that's what happens in this line. And also I printed this just to check the things, but this is again a bad practice, so we have to comment this out. But if you want to check it yourself or adjust the code, you can keep it there. But if you finished everything, or when you finished everything, just get rid of these and comment them out. So this part is done, and the only thing that we have to do is see what we do with this show LCD function. And this is again a very short function. So first of all, when we enter this function, we have to check if 200 milliseconds is elapsed. If not, we just skip everything. But if 200 milliseconds is elapsed, which is the update frequency of the OLED display, then we enter this part. And what this part does is the following. So it checks if the number of clicks has changed. So if we moved the encoder or not. So if we move the encoder, then these two numbers will not be equal. And that means that we can enter this part and update the screen. So what happens here is we erase the screen, and then we print the current number of clicks, and then we update the timer. So that means that this 200 milliseconds timer starts over. So we have to wait again 200 milliseconds to be able to check this if condition. And we also refresh the previous number of clicks with the current number of clicks. So that means that, for example, we were at 100 clicks, then we print 100 here, and also update this to 100. So when we move the wheel again, and whether we go to 101 or 99 by just clicking it with one step, then this condition will be true again, because the current number of clicks, which was changed here in the interrupt, will not be equal to 100. So then we can enter this again. So this line makes sure that we keep the most recent value of the position of the stepper motor in this part, and whenever we change the position of the wheel by running this interrupt function, then these two values will not be equal, and we can run this function again. And coming back to the loop, the main loop, what happens here is that we just always write the number of clicks here, and since this is an absolute movement, if we keep writing the same number in the argument of this function, nothing will happen, because the stepper motor will not be instructed to do any movement. But if this number differs from the previous number, then we just run to that position. And in fact, since we move one by one regarding the steps, so this thing runs very, very fast, this loop, then the acceleration will not play any or too much role. And also I did some mistake, because this should not be here, because that we don't even use this. I used it in a previous example, but I noticed it too late. So you can see that this is a very simplistic code, and the whole code is basically 100 lines. I have too much line breaks here and there, so this is roughly 100 lines. So it's not a big challenge. So I will upload this code to my website, as well as the circuit schematics. So please check my website, curiousscientist.tech, and also check the description of the video, because I put a lot of information there, and you will find a lot of things there, so always check it. If you have any questions or suggestions or something, please let me know and write it in the comment section, so I will try to answer that. I have some future ideas with this kind of encoder wheels, and I will soon start uploading those videos as well, so stay tuned. And I hope you liked this video, I hope you learned something, and see you in the next video.